Hello guys, in today's video we are going to talk about simple pendulum. Now what is simple pendulum? Simple pendulum there are, its name is simple pendulum, but then the assumptions that we make, that may not sound to be that simple. Okay, now what are the assumptions? Number one is the bob is heavy, okay, and when we say heavy, it is heavy compared to the mass of the string. Okay, and I have this fixed or rigid support here, and this pendulum is over here. Now this string, even if it doesn't look straight, it is straight. Okay, and this is the bob of mass m. Okay, the string, there is some tension in the string here. Okay, now the assumptions. Okay, the string is massless. Okay, the string is inelastic, the string is inextensible, there is no air resistance, correct? So what are the assumptions? The string is massless, the string is inelastic, inextensible, the friction at the support, okay, the friction at the support here at point O here, it is 0, okay, no air resistance. So all the ideal conditions, right? And so that is what gives us a simple pendulum. Okay, now with these assumptions, okay, now we are going to make this pendulum oscillate. Okay, so I just displace it to, let us say, this position here. Okay, and I'll leave it. Okay, this displacement is x. Okay, now in this position, okay, won't the weight act vertically downwards here, mg, correct? And would the tension be T here? Yeah, tension is T. And let us have this angle theta. Okay, now this theta is a small angle. Okay, when I say small, you would ask how small. So I would say very small. Okay, it's like if theta is equal to something, something between 0 to 10 degree, okay, 0 to 10 degree, it's called a small angle. So let us keep that angle small, okay. And now what happens here is, if I resolve this weight, okay, along the string and perpendicular to string, then I would have something like this here and something like this here, correct? And then this angle is theta, so this component is obviously going to be mg cos theta, and this will be mg sin theta, correct? Now look at this carefully. Okay, the component of weight, okay, the component of weight acting along the string is mg cos theta, and perpendicular to string is mg sin theta. Now there is something here, this pendulum, okay, this bob, it tends to come back to the initial position. Let us call this position O. Okay, from position A, it tends to come back to position O. And what is bringing it back to the main position? Is it not the component of weight acting perpendicular to the string, right? So mg sin theta is the restoring force acting on the bob. Okay, so I'm going to write here F is equal to mg sin theta, but then it is acting in the opposite direction, so I'm going to put this sign, negative sign here, correct? I have said that theta is a small angle. Okay, for a small angle theta, you can even check it on your calculators. Take a small angle, let us say 1 degree. Okay, convert that 1 degree angle into radian. Okay, so and then find out the sine of that. Okay, sine of 1 degree, and what is 1 degree in radians. Okay, express 1 degree in radian. You will find that theta is equal to sine theta. For small angles theta, sine I'm going to write it here. For small theta, sine of theta is equal to theta. Correct? So this becomes f is equal to minus mg into theta. Correct? Minus mg into theta. Now what next? I have to prove that this is simple harmonic motion. Okay. What was my displacement here? Wasn't the displacement x here? Or then the length of arc described? Okay, that arc length was x here. What is the length of pendulum? Length of string? Or then when I say length of pendulum, it is the distance between the fixed support and the center of the bob. Okay, and then that length, I'm taking that length as L. Okay, so I have x here, arc length is x, and L is the length of the pendulum. Okay, and then what was my angle when I displaced the bob by x? The angle with the vertical is theta. Correct. Now here, don't you remember this? I have this circle of radius r, and if I have this angle theta, and then this is my arc length s, then s is equal to r into theta. Correct? Now here, my arc length is x. My radius r over here is that this is my L is the radius. Correct? And angle is theta. Correct? So can I use this? Yes, I can. So I can say that my theta is equal to x upon L. Correct? Just try to figure out the analogy between this and this. Okay, this point is fixed, my radius or the length of pendulum is fixed. Correct? So that I am taking as radius. Okay, and then theta is the angle, and then this displacement x, that is my arc length. Correct? That gives me this theta is equal to x upon L. So why not substitute over there? Okay, so my f is equal to minus mg into x upon L, or then I'll write this as minus mg upon L into x. So that is my f. Now here you would see that mass of pendulum, it is constant, acceleration of free fall g, that is constant, and length of pendulum is constant. It's not going to change anyway, right? So my force is proportional to the displacement. Correct? So I can say that F is proportional to minus x. Force is proportional to displacement, and it is acting in the opposite direction of displacement, right? So that means this is some condition which is needed for simple harmonic motion, isn't it? So but then when is this true? This would be true only when I'm able to use this, and I'm able to use this. Theta has to be small, number one, and only then I can substitute that theta is equal to sine theta. So it won't be it won't happen that you take this pendulum and hold it like this and leave it. Okay, no simple harmonic motion. Okay, you cannot expect that to be simple harmonic motion. We have to have certain conditions satisfied, and then yes, you can have your pendulum perform simple harmonic motion. Now coming back to this. Okay, now what is my force? Is it not mass into acceleration, Newton's second law of motion? So m into a is proportional to minus x here, and a would be proportional to minus x, because again my mass is going to remain constant. So or then F is equal to minus m into gx upon L, or I can say a is equal to this part gx upon L. Is it not my acceleration? So acceleration is gx upon L, or minus of gx upon L. Correct? Alright, now since we have said that this is simple harmonic motion, what is the condition for simple harmonic motion? My A is equal to minus omega square x, correct? A is equal to minus omega square x, and here my A is equal to minus gx upon L, correct? So what can you infer from this? Okay, if you compare 1 and 2 here, can I say that omega square is equal to g upon L? Can say that, right? Or omega is equal to root over g upon L? Yes, we can say that. But then what is my omega? Is it not 2 pi upon t? 2 pi divided by periodic time of SHM. So 2 pi upon t is equal to root over g upon L. So I can say that t is equal to, I take this t on that side and this whole thing on this side. So t would be equal to 2 pi root over L, capital L it is, upon g. And this gives me periodic time of a simple pendulum. Okay, and I think you might recollect this, we have used this expression in earlier classes. Okay, the periodic time of a simple pendulum is equal to 2 pi root over L upon g. Now there is something called seconds pendulum. Okay, now what is a seconds pendulum? Seconds pendulum is a simple pendulum which has got its period is equal to 2 seconds. So what does it mean? I have this mean position here and I displace it to some position there. Okay, now when I leave it from this position it goes back to the mean position, moves further and again comes back and comes to the same position from where I left it. That means it is that is one period, right? And that one period takes 2 seconds. That means 1 second from here to here and 1 second for returning to the same point. That is called seconds pendulum. Then so that means that the period time of seconds pendulum is 2 seconds, correct? You substitute 2 over here, okay, and then 2 would be equal to 2 pi root over L upon g, and if you substitute g is equal to 9.8, okay, you would get the length of seconds pendulum would be something like 0.9912, or something like that. So approximately it is 1 meter. If you have a simple pendulum of length 1 meter, then the periodic time would be 2 seconds, and that would be a seconds pendulum. One more thing that you could make out from here is, can you see any mass, any term involving mass over here? No. So if you have a simple pendulum of mass, let us say 10 gram, okay, and you measure the time period, okay, and then keeping the length same, okay, you increase the mass to, let us say 500 gram, okay, and measure the time period, it is going to be exactly the same if you ignore the air resistance. Okay, so it is the periodic time of a simple pendulum is independent of its mass. It only depends on the length of pendulum and the value of acceleration of free fall at that place. Okay, so that means if you are on equator for the simple pendulums of all the lengths would or same lengths, but then different masses would have same time period, okay, on equator. But the same pendulum, if you take to maybe North Pole, then the periodic time would be different because the value of g over there is different, correct? So these are a few things about simple pendulum. In the next video we are going to talk briefly about damped oscillations, or we'll discuss briefly about free oscillations and damped oscillations, and we'll figure out the time period and amplitude of damped oscillations. Thank you so much.